Okay, in this podcast we're looking at the review for Unit 9. So it says convert a pressure of 635 millimeters of mercury into the corresponding values of atmospheres and kilopascals. Okay, easy enough. So 635 millimeters of mercury, and what I know is if I'm going to atmospheres, I know one atmosphere is 760 millimeters of mercury. If I divide that out, I get 0.836 ATM. Okay, 3 sig figs, just like what I was given here. Now, if I also can go to pascals, kilopascals. I 635 millimeters of mercury, and what I know is both 760 millimeters of mercury and 101.3 kilopascals are standard pressure. So this is going to give me 84.6 kPas. Alright, let's take a look at number 2. Number 2 says you have a cylinder that's 22 liters. It has helium in it, 150 ATM, 31 degrees C. What will be the volume at a different pressure and temperature? So this is a changing conditions. So I want to make a table. I've got 22 liters. I've got 150 ATM. I've got 31 C, and I'm just going to add 273 to that, and that's going to be 304. Okay. And the question is, what's the new volume? If the pressure becomes 0.99 ATM, boy, that's a big drop. And the temperature becomes 22. So 22 plus 273 is 295 K. Okay, it's a pretty straightforward problem. I have 22 liters, and this is my pressure, this is my temp, my volume. My pressure is going way down, which means my volume will go way up. So I want 150 over 0.99. They're both ATMs. And if my temperature is going down, my volume will go down, so I want 295 over 304. And if I multiply these out, I get in 2 sig figs, which is what I need because I have 31 degrees. It's going to be 3,200 liters. Huge difference in volume because of the tremendous change in pressure. Okay, so now it says I have a helium-filled balloon. Balloon was launched at 22.5 degrees C and 754 millimeters of mercury. If the balloon's volume was 4190, what will the volume be at 20 miles with other pressure and temperature? So this is again a change in conditions. So I'm starting with 22.5 degrees C plus 273, that's going to be 295.5 K, and 754 millimeters of mercury, and let me see, 754 millimeters of mercury, and oops, I missed here, 4190 liters. Alright, and want to know the new volume at 20 miles where the pressure is 76 millimeters. Again, a huge drop in pressure, and the temperature is minus 33. So 273 minus 33 is going to be 240. So temperature, pressure, volume. I'm looking at what happens to my volume. I start with 4190 liters. Okay, let's look at temperature first. Temperature goes down, so my volume will go down. So I need 240 over 295.5, so that will make it go down. And my pressure is going down, way down, so my volume is going to go way up. So this is going to be 754 millimeters of mercury over 76 millimeters of mercury. If I multiply this out, I get 337. I need 2 sig figs, so it's 34,000 liters. Huge difference. One more time. Alright. If you have a sample of a gas in a rigid flask means the volume can't change. And the volume's 250. Okay, so I've got 250 milliliters. Pressure 25.5 gas is at 360 millimeters of mercury. If I decrease the temperature, what's the gas pressure? Okay, so my volume's going to be the same. I'm changing my conditions of temperature, so I start at 25.5 plus 273. That's going to be 298.5 K, and I have 360 millimeters of mercury. I drop the temperature to -5. If I add that -5 to 273, I get 268 K. And my question is, what happens to my pressure? This is a very simple problem because, again, volume is constant, it's rigid. So I have 360 millimeters of mercury, and my temperature is going down, so my volume should go down, 268 K over 298 K, and I get 323, so it's going to be 320 millimeters of mercury for 2 sig figs. Okay. Okay, so explain in terms of energy transfer why the alcohol level on a thermometer rises when it's placed in warmer fluid. We haven't talked about this, so I'm not going to put it on the test, but basically what you have in the thermometer is you have all these particles, and as it heats up, they are moving faster and faster, and as they hit each other, they transfer their energy. So first the flame under the beaker transfers heat to the beaker, which transfers heat to the water, which transfers heat to the bulb of the thermometer, which transfers heat to the particles, which transfers heat to the particles it hits, and so on and so on. Okay, number 2. Explain why the Celsius thermometer scale is not appropriate to use when describing the behavior of gases. That's because we can't use it to predict. In the temperature was degrees C, and we're looking at what's happening to either volume or pressure. We have a relationship like this where it's a large y-intercept, so we can't make any general claims. We can't say if I double temperature, I'll double volume or pressure. Okay, so I need to use temperature Kelvin, because the Kelvin scale was developed in order to provide a directly proportional relationship between temperature and volume or pressure. Alright, so let's take a look at number 3. Suppose you lower the temperature of a gas from 100 to 50 C. By what factor do you change the volume of a gas? Okay, so that's going to be a temperature factor. I'm going to go from 100 C, which is 373 K, to 50 C, which is 323 K. So my temperature goes down, my volume will go down by this factor, 323 K over 373 K. And if I multiply this out, I get 86.6%. So it drops by about 13%. Not very much, even though I'm halving my Celsius temperature. But if I lower the temperature 50% in half Kelvin, what factor do I have? Now I'm going from 100 K to 50 K, temperature going down, volume will also go down, so it will go down this time 50 K over 100 K, which will be 50%. Big difference. Okay? So if I cut my temperature in half, I cut my volume in half. That's what the proportional relationship, directly proportional relationship, allows us to do. What's the equation we use to describe gas pressure? Pressure in general is equal to some force over some unit of area. Alright, so how does a barometer and a thermometer work? Okay, so I'll talk about the original barometer. So it's in this pool of mercury that's open to the atmosphere, and there's this tube, and as the pressure from the atmosphere pushes down on the surface of the mercury, it forces the mercury up this tube, which also has a weight of mercury pushing down. So it's kind of this tug-of-war between the pressure of the atmosphere and the weight of the mercury, and wherever the mercury level ends up is what's red, and it's red in millimeters of mercury. So the higher the pressure outside, the higher the level of mercury will arise. Okay, what's happening with thermometer? I'll talk about Anders Celsius and what he did. So he developed the thermometer, and what he did was he noticed the some materials would expand when they got heated, so he put mercury in a test tube, put it in a beaker, and when it was at its freezing temperature, he called that 0 degrees C, heated it up. When it got to the point where water was boiling, he called that 100 C, and that was the boiling point of water. Okay, he gave his own name to the temperature, C. So the next question is, what happens, where is atmospheric pressure, Mount Everest or New Orleans? And the answer is the pressure is higher in New Orleans, because if you imagine drawing a map, you got Mount Everest up here, you got New Orleans down in a valley. New Orleans, Mount Everest, much lower altitude. If you think about pressure being a column of air above you, the column of air is going to be much larger here in New Orleans, much more pressure. Okay. Describe the relationship between the variables. Pressure doubles, volume halves. We know pressure is directly proportional to 1 over the volume, the inverse of the volume. Pressure is directly proportional to moles, which means I double one, I double the other. Pressure is directly proportional to temperature if it is in Kelvin. Again, I double one, I double the other. And volume is also directly proportional to temperature, assuming the temperature is in Kelvin. Okay. So the next one asked me to draw graphs of what these relationships look like. In all cases, we want to put pressure on the y-axis. So what I'm looking at is pressure, and I'm putting volume here, and this is an inversely proportional relationship, which is one of these curves, something like this, right? If I have moles and pressure, it's a directly proportional relationship. As I double the number of moles, I double the number of pressure, the amount of pressure. Temperature in Celsius, it's not directly proportional, it's a large y-intercept. So this is temperature, degrees C, and this is pressure. It's a linear, a positive linear, but not a directly proportional relationship. Whereas temperature in Kelvin, versus pressure is a directly proportional relationship. It goes to the origin. Alright, number 10. Draw particle diagrams for each of the following conditions. Okay, constant moles and temperature, and I've got 1 liter, and I've got 4 liters. Okay, and constant moles, 1, 2, 3, 1, 2, 3. Same temperature, same size whooshy. So the question is, which will have the higher pressure? And the answer is this guy, because each, pressure is force per unit area. I've got the same amount of area to hit, but I got a lot more force because they're hitting more often. So the pressure will be higher in this box. Okay. At constant temperature and volume, so I want same size box. Constant temperature, 2 moles versus 4 moles. So 2 particles, and we'll do 4 particles. And I meant to make those the same size. Constant temperature. So the whooshies are the same length. And the question is, which has higher pressure? Well, of course, this one does, for the same amount of area for the particles to collide with. They're getting twice as many collisions because there's twice as many particles in this one. Okay. Here we have constant moles, constant volume, so the same size box. Same number of particles. I'll make 3 in each. This has half the temperature. Make the whooshes longer here, whooshes longer there. Okay. So higher pressure, of course, is going to be here, because if they're going faster, they're going to hit the walls more often, causing more pressure. Okay, and the last one here is at constant moles and pressure. Okay, so if moles are constant, pressure is constant, but I'm doubling the temperature. The only possibility is that I must double my volume. So I've got two particles here. I'm going to have 2 particles here. And if I'm going to get the same pressure, I must be hitting the same I must have the same force per unit of area, and the only way I can do that is if I make the box bigger. Okay, that's going to do it.